A very good morning, everyone. Welcome to the November for which we have the IMechE SEAR webinar that is being held on the very bright sunny morning here down south. I am Yan, the associate professor from the Newcastle Australian Higher Educations in Singapore, and of course a member for IMechE, and today I'm your moderator for this particular webinar. And of course today we are going to talk about development of 4D printing technology and its contribution to the sustainable development goals, for which we do have our very distinguished Associate Professor Kushendarsyah Saptaji to be our speaker for today. And before we get ourselves started, let me introduce Prof. Saptaji to you from his biodata here. Associate Professor Kushendarsyah Saptaji is currently the head of a mechanical engineering study program at Sampoerna University. Prof. Saptaji is a chartered engineer and the Indonesia country representative for IMechE. He holds a doctorate from Nanyang Technological University, Singapore, and previously served as a senior lecturer at the Faculty of Manufacturing Engineering, Universiti Malaysia, Pahang from 2015 to 2019. His primary research interests lie in additive manufacturing, machining, and material science. With over 70 international publications, his work extensively covers the application of 3D and 4D printing in medical and industrial sectors, alongside the integration of AI and sustainability into manufacturing processes. Beyond research, Dr. Saptaji has extensive teaching experience in core mechanical engineering subjects, including manufacturing processes, additive manufacturing, materials engineering, and engineering design. He has successfully supervised dozens of final year project students and numerous other initiatives. His professional experience also includes works of failure analysis and ceramic materials. Currently, he serves as a chief editor of Indonesian Journal of Computing, Engineering and Design. So without further ado, let us welcome Prof for our seminar today. Prof, the floor is yours.
Thank you, Prof. Ko. Good morning, everyone. It's very honored to be here to deliver webinar 1 for IMechE Southeast Asia region. So I will start my presentation. Is my slide? Can you see my slide now? Okay.
Yes, we can see your slide. Yep.
Okay, thank you. Okay, so my topic today is about 4D printing technology, and we will see some background about 3D printing first, and then some result related with 3D printing. After that, we will go with 4D printing technology, and then we will see some result related with 4D printing technology that we have done so far. This is my brief introduction, which already mentioned by Prof. Ko. Maybe I will go directly with the topic. Okay, so as you know, maybe most of you already familiar about additive manufacturing, which is also we sometimes call it 3D printing. 3D printing is technology that create 3D structure. We call it additive manufacturing because we add the material layer by layer. Yeah, in contrast with the machining, which we remove the material. So the product that produced by additive manufacturing, normally it is value dense product or high value with small quantity volume, which is also, we can call it mass customization. So normally by using 3D printing, we can customize the design. We can make a more complex structure compared with other manufacturing process, and also we can make it a product with low cost process. And we can also use these to produce a small size features, like for example, some component that used in the microfluidic, for example, microfluidic technology. 3D printing become more important because this is part of the Industrial Revolution 4. We can see in here there are various technology related with Industrial Revolution 4, and one of them is additive manufacturing. So that's why now this technology is getting more interesting and also become growing very fast. The process of 3D printing is basically, we can see in the simple explanation in here, where you basically designing a product using CAD software. And then after that, once you approve this design, normally you can convert into STL file, and then you process with the 3D printing process to become the product. There are many 3D printing process that are available, but I will highlight only two in here. The first one is, which is already common for us, which is the fuse deposition modeling of FDM, we call it. So in FDM, basically, we have a filament. Normally, this is plastic filament, and then it will be roll, and then after that, it will pass through a heating chamber inside the extruder, and after that, the plastic will melt, and then it will create a product in 2 dimension. Once it is finished, and then the base plate will move, or this the nozzle will move up. Okay, so this is like I mentioned, layer by layer process. So now there are many available and affordable 3D printing machine available in market. This is in Indonesia rupiah. So from the low cost, even now to the high cost like this one. So compared with the last maybe about 7 or 8 years ago, there are not many 3D printing available in the market. Now you can see and you can buy many type of 3D printing in the, especially in the online market, like FDM from Bamboo, from Anycubic, from Creality, Lego. Yeah, there are many brands offer different kind of 3D printing. The second process that I want to show in here is stereolithography, or SLA process, and also which is similar with digital light processing, or DLP. So in this process, basically we use laser or light from the bottom, and then the raw material in here is resin, and the platform is at the top. So once one layer finish and then solidify, then this base will move up. So then the layer by layer is created in this inside of the resin. You can see the illustration in this video. Yeah, that now the resin 3D print also is quite common. It's available in the desktop size, so it's again affordable machine. In here, I will show some application of the 3D printing. Mainly, as you know, it is used in engineering component, it shows in this slide shows one of the example used for fuel tank for the Terran 1 rocket. Yeah, so it can be used to make not only small but also big component. Sorry. And then here also show an example of the car produced by 3D printing. Most of the component in here are 3D printed. As you can see, the layer by layer can be seen in this body of the car. The more important application of 3D printing is in help in human life is to make an implant. So here's some example of the 3D printed product. For example, here is the titanium alloy implant for the skull, and then this is for pelvis. Yeah, the process used in here is direct metal laser sintering, where the raw material is basically a powder of metal, and then it will be layer by layer solidified by using laser. And some other example in here for orthosis, and then for wrist spline, and there's also technologies try to develop 3D print for the heart, like this. Yeah, so yeah, still ongoing. Some other example for joint hip prosthesis in here. Yeah, most of the component in here are made from 3D printing. For example, the cup using electron beam melting. In here is the part of the implant, the femoral stem, produced by direct metal laser sintering also. 3D printing also now used to build the house, to build a building. Yeah, so it's combination of maybe mechanical engineering with civil engineering. I think in Singapore they already built one. For food also, we can use 3D printing for making food. For example, like this. This is artificial meat. This is some candy or snack. It shows the restaurant in I don't know, maybe in France. All of the component and food in here are made from 3D printing, and maybe in the future even we can have a 3D printed at home that can print our own food. Yeah, so mainly the application in 3D printing food now is for hospital need, where we need to control certain amount of mineral or vitamin for the patient. For astronaut, they use 3D printed food. Yeah, and now many applications also can be used as well. Next, I will show some result from our research that already published related with the 3D printing technology. The first one, we have done this research where we basically use indirect additive manufacturing to produce lumbar spine model. So this model is used for practice for the doctor who, before going to the real surgery, they can do some practice using this model. So in here, the step that we have done is basically we scan the patient lumbar lumbar part of the spine, and then after that we create the mold using PVA filament using this parameter, and then we do the casting. That's why we call it indirect additive manufacturing, because we use 3D print actually to create the mold. So then inside of that PVA mold, we have a space where we inject PU foam like this. So we drill the mold, and then we inject the PU foam, and then we let it for curing for about 48 hours or 2 days. And then after that, we dissolve the mold because PVA is can be dissolved in the water. So we keep it inside water, and then the mold will be dissolved. Then we will get the um, the lumbar spine model made from PU. Okay, so this work has been successfully produced lumbar spine model, and then we also have published this in the journal. The second work that we have done is basically we create ankle foot orthotics. So in here, we based on the data, basically the injured due to the ankle foot orthotic is quite high. So in this work, we create the orthotics first by again doing the 3D scan, the patient ankle, and then we convert that 3D scan model into the 3D mesh model. And then after that, we adjust the model using SolidWorks. And then we come out with the design of the ankle foot orthotic. And then after that, we print using FDM process. And once we get the 3D print prototype, we perform the test using guide analysis. And from there, we get some conclusion that the angle of foot and calf maximum error is about 18%, which is good. And then with this process, we can reduce the cost compared with the conventional method using a GIPS normally. And processing time also can be faster, like about 41.5% compared to a conventional method. This work also has been published in the Q4 journal. The third work that we have done is we try to create a 3D print machine for food material. So basically, we modify the existing 3D print machine, and then we change the nozzle with syringe and also stepper motor. So with this, the raw material that we use in here is basically strawberry jam and peanut jam. So we can see the video in here. So this is the machine that we modify. We try to print the strawberry jam. Okay, so by modifying the machine, and we measure the dimension of the printed gem compared with the design. Basically, there's still some error, like the diameter and the side error is about 3.86% and 6.91%. So this is for the circular shape, and this is for the rectangular shape. And there's an error also in the height, which is quite high. So we still need to improve this. However, this result also has been published in a conference only about 2 years back. The next result that I want to show is about we try to optimize SLA 3D printed using additional HNT material. Yeah, so we try to create a mold, master mold for the hot embossing application. So for this work, we have 3 resin that we evaluated, and then we we perform the thermal test for this 3D resin, and we also perform the mechanical test. From the mechanical test, we get that the high temperature resin has the best performance, and so then we use this resin as the resin that we will add with the HNT. So then we prepare the HNT, which is Halloy nanotube, and then we do the mixture, and then after that we perform the test again with additional 1, 3, and 5% of HNT to the high temperature resin, and we compare the result here that there's improvement of the mechanical properties compared with the standard resin. And after that, we created the mold for the hot embossing, and we performed the hot embossing test using this machine, and we get some good result, which for the 0% additional of HNT, it's basically the mold was broken after a few times of embossing process, but for this 3%, it produce a good strength and also good performance where it can be used for a few times. So this result also has been published in this Progress in Additive Manufacturing journal only about this year, beginning of this year. So that's all about 3D printing technology that we have done, the research that we have done with related with the 3D printing process. Now we move to the next process. So after 3D printing, is there any 4D printing, or is there any 5D printing, or is there any 6D printing? So basically this question raised when we talk about 3D printing. So basically, what is 3D or 4D printing technology? You can see the comparison between 3D printing and 4D printing in this slide. So 3D printing is basically you have material, and then you do 3D printing, and you produce a static structure. While in the 4D printing, what you use is smart material, and then you perform 3D printing, but you have to add some or you have to create the design that can be dynamic. Yeah. So once you print, you will get only static structure similar, but because we use smart material, so we call it smart static structure. And then after that, with this structure, if we add some stimulus in here, we will get some smart dynamic structure, or we can add some interaction mechanism. So that is the difference between 3D printing and 4D printing, where the material that we use is basically, we call it smart material. Not all material can be used for 4D printing. And we create smart static structure, not only common structure, and also we add some stimulus in order to have the 4D printing effect. So this is basically the concept of 4D printing. So the concept of 4D printing is basically introduced in 2013 in Tech Talk by T-Bits. So from there, the initial definition of 4D printing is basically we have 3D printed with stimuli or responsive material. So the fourth D in here is basically time. So we have the 3D structure, which is the structure in X, Y, and Z. And we have additional D in here, which is time. So in certain time, or by having certain period of time, we can modify or we can have a different structure that we already created before. And then the concept of four dimension now has been involved, the shape, the properties of the material, or the functionality of the 3D printed object that can change over time under external stimuli. There are many stimuli that we can use in here, such as heat. When we heat up that 3D printed structure, then it will change, or use light, humidity, water, voltage, and pH. So many external stimuli that we can apply. So it's basically, the concept is like this, yeah. So you can use different type of stimuli. The results of 4D printing also now is increased. As you can see, this is the data from 2018. It's quite long data even. So the publication is increased. Yeah, this citation also increased, and then the publication mainly from USA, China, Singapore also has, and then the printing technology that used is basically mainly FDM. So the simplest 3D printing process can produce 4D printing, SLA, inkjet, DIY, or SLS and DLP. So schematically, you can see what is 4D printing in this slide. The printing technology that we can use is this one. The material that we can use, many type of material, SMP, which is shape memory polymer, shape memory alloy for metal, hydrogel, ceramic also can be used, support materials, and also elastomer. And this is the stimulus. Many type of stimulus we can use, and also the type of programming, whether you want to make it into two shape, multi-shape, or one-way actuation, two-way actuation, color change, or self-healing. So let's now move to the materials. The first thing that you have to consider when you want to apply the 4D printing. So basically, the material is similar like if you use memory pillow, if you know about memory pillow. So basically, the concept is similar with this memory pillow. So when we use as printing technology is FDM, normally we use the polymer material. So one of the polymer material that you can use is shape memory polymer, SMP. SMP is one of group of polymer that can change to temporary shape and return to initial shape under external stimuli. So the external stimuli, as I mentioned before, can be temperature, light, electric field, magnetic field, pH, or ions. Compare with SMA or shape memory alloy, which is made from metal, and SMC or shape memory ceramic. SMP has more advantage. So because this is polymer, normally the deformation is larger. And also we can adjust the glass transition temperature, which is normally below 100 degree. And we can also use different actuating mode. This is also lightweight, yeah, because polymer is lighter than metal and also ceramic. So the popular SMP that normally use, the first one is polyurethane, and also the PLA, which is the basic filament that we use in daily life. Yeah, if you work in 3D printing, normally PLA is the common material to print your product. While for SME is nickel titanium or nitinol. Yeah, nitinol is one of the shape memory alloy, okay, or copper, aluminum, nickel. So more detail about SMP in here, we can see in this slide. It's basically SMP have glass transition temperature. So if you see the the graph in here showing the specific volume in y-axis and the temperature. So before melting, there's one point where the polymer change, which is glass transition temperature. So in here, when the temperature increase, so the polymer will change from glassy state into a rubbery state. So that's why, for example, for PLA, when we heat up this material beyond its glass transition temperature, the material becomes soft, become rubbery. Okay, so what happened in that transition is basically the specific volume change, like this, and then beyond this you can activate the shape memory effect or the shape change. However, below this, the internal energy of polymer chain is low and they cannot move freely. So once it reach the glass transition temperature, then the material, the SMP material, will be rubbery and soft, and also it is easy to deform. So this is the explanation basically. Okay. In SMP itself, it's also divided into two types of material. One is amorphous. We can see in here, the amorphous is basically the state of material change gradually in response to heat near TG, and semi-crystalline SMP. So in semi-crystalline, the state of material change rapidly near plus temperature. So we can go back to here. So this is the semi-crystalline solid. So basically there will be some significant change, near the TG for semi-crystalline. Well, for amorphous, it's only gradual. So we can also see from here, from this graph, where the x-axis is TG and the y-axis is the Young modulus. So at TG there is a change. Beyond TG there is a change in the value of ER. So then it become lower, or it is become softer. So that's why the PLA, for example, change its behavior beyond of TG. Okay, so basically we can go back to this original shape by again heating up the material. This is some application or some example of 4D printing stimuli. This is using moisture. So we can create a gripper using moisture stimuli. For example, this gripper. So the printed structure absorbs moisture, resulting in swelling and distortion. So this is normally used for hydrogel material. We can use for this kind of stimuli. The second one is by light. You can see in here. So the objective in here is to obtain the best color of light as stimuli to control the shape modification. You can see, for example, if you apply red light, okay, and then this structure will change. Initially it is flat, and then you apply red light, and then it change like this. And then when you apply blue LED or blue light, then it become to the initial state. You can also do differently. For example, you apply the blue light first, you will get U shape like this. And then when you apply red LED, it will go back to the initial state. So this kind of stimuli, which is using light, you can change the shape of the material. So yeah, this is used for the material that can absorb light. So then inside of that polymer, there will be some chemical changing due to the effect of the light. Another which is common also stimuli is the heat stimuli. This is the example of the gripper. Yeah. So basically you print the gripper like this flat, and then after that you heat up normally inside the hot water, then it will soften. Yeah, and then it will bend like this. Yeah, so this bending it depends on the structure of this printed. Yeah, you can see in here this researcher print different pattern for the gripper. Yeah, then they investigate the effect of this pattern. Yeah, so the test that they have done is basically they put the sample inside of the hot water. It's about 85 degree, where at 85 degree is SMP, especially um, PLA is already softened, and then uh, they push this, and then they will grip the object, and we can take out the object from the hot water, and at room temperature, this gripper is already hardened, so it still can grip the object. So this is the stimuli by heat. So for from those explanation, there are many application in industry for 4D printing, like in biomedical, yeah, for drug delivery, for example, for tissue engineering, for biomimetic, like soft robotic. Yeah, now there are many researchers doing this. Yeah, so like this one for the gripper, soft robotic. For microfluidic also we can use, and for medicine also we can use for the printing. Besides that, there are many other application of for the printing in gripping. Yeah, this is a small gripper. It's about, you can see the scale in here. It's about 5 mm, so it's quite small. So it is hit up by wire. So and then it becomes soft, and then after that it can grip the screw like this. Yeah, or you can use for orthotic, prosthetic. Okay, so this one is stimuli by moisture. Uh, this is another example of actuator. Yeah, you can produce this by using heat. Yeah, this is for the printed by combination two different material. So one is not SMP and the other one is SMP. Then we can combine into a certain gripper. This is the last example that I want to show is basically for a medical application, where it's basically you can take a clothes in the inside your body. It will take a blood clot inside the what do you call it, the vein, yeah, of blood circulation. So basically we apply this, and then this blue color will change the shape, and then we can pull this blood clot from our blood circulation. So then this is one of the application. Another application, this one is for wound closure. Yeah, so you can heal if you get injured using this kind of application. Okay, now I'm going to discuss some of the research that I have been done with my student in here. Some already published and some is in the process of publication and in the process of submission related with the 4D printing. The first work is related with we try to optimize the parameter of 4D printing for PLA using different parameters. So this is the design of experiment that we plan for the 3D printing parameter. We differentiate the infill density 50% and 100%. We want to see what is the effect of infill density and also the printing speed. While the parameter that related with 4D printings are we want to see the effect of the thickness and also the deformation temperature and the recovery temperature. So after we apply the heat, we want to recover back the sample into the original or the initial shape. And this is the parameter, and then this is the specimen that we created. We created the N shape or the semicircular shape like this for different thickness and for different printing parameter, which is the infill density and also the printing speed. After that, we put in this is the oven that we use to heat up the sample. So this is the flow of the experiment. So we print the specimen into semicircular shape, and then we heat up inside the oven. And then after that, we apply load at this temperature, which is at the oven temperature, 5 kg load. And then we expect it will go back to the original, to the flat shape like this. And then after that, we recover back the sample into the oven by heating up into this temperature TR. And we measure what is the final shape, whether it goes back to this shape or not. So then we measure this, the initial deformation and the final recovery deformation as the recovery ratio. And we perform the ANOVA analysis to get the optimum parameter. So this is the plot showing the recovery ratio with respect with time. Yeah. So we measure at different time for different printing speed. Okay, this is for the 50% density, this is for 100% density, and this is the specimen after deformation and loading stage. So it will be like this. Yeah. So meaning at this stage. Yeah. Okay. So not all sample are straight. There's still some curve in here. And this is the for the 3 millimeter thickness. This is for 6 millimeter thickness, and this is for 1 millimeter thickness. So we measure the recovery ratio for each of the time and each of the thickness and for different printing parameter. And from here, we can get that the PLA structure that we have created had the optimum shape member properties with the combination of if we apply high recovery temperature, which is TR, if we apply faster printing speed, lower density, and also smaller thickness. So then at smaller thickness, the recovery will be better compared with the thicker sample. This work also has been published in Progressive in Additive Manufacturing only 2 years back. The second research that we have conducted related with the 4D printing is we created a 4D printing gripper. So we want to know the effect of the finger design and also the effect of the thermal stimuli So this is the flow of the experiment that we have conducted. So we create the 3D design of the finger. After that, we print and we apply the heat stimuli, yeah, using hot water. And then we measure the bending of this finger. And then we need to find which design is the highest or the best bending. And then after that, if we get that, we create the full gripper and the design, and then we test that full gripper to grip different shape and different material of the object. So the first step that we perform in here is basically we compare 3 different cross section. So we have triangle cross section in here. This is the side view. The cross section is, if we can see from this side, we can see the cross section. This is the semicircular, and this is the rectangle cross section. So from this, we can see we decided that the rectangle cross section is the best. So we continue with the rectangle cross section for the next research. And then after that, we decided the cross section, and we need to find the best combination of the fin. This is the fin, and also the gap. So we have 3 specimens with 3 different fin thickness and gap distance. So this is the fin thickness 1 mm, the gap distance is 1 mm. This is fin thickness 1 mm. The gap you can see is more, which is 3 mm, and this is the thicker fin, and this is the more gap. Yeah. So from these 3, we found that the best one is this one in the middle, because from the analysis that we performed, this is the maximum deflection, but it is shorter. You can see this is maximum deflection, but also it's shorter. So the best one is this one, which has the longer specimen, where the objective for this is we want to grip the object. We also curious whether the fin give effect or not. So we also print the specimen without the fin. So here we can see the fin helps in bending result. So we continue with the fin. After we decided that is the best design, then we created the full gripper like this. So in here we print using PLA, the material, which is the smart memory polymer, and the shaft in here is made from ABS, which is not the SEC memory polymer. So then we test the gripper in here, and see, this is our test. This is hot water at 85 degrees. So you can see the SMP now is softer. And then we grip the object. We keep it a few seconds until the material become hardened again. So the temperature is reduced. So you can see now it become hardened, then it can grip the object. Okay. So we perform some tests for gripping different object and different shape. Yeah, for example, this is cylindrical made from metal. This is trigonal metal, and this one is made from plastic. And also we tested by gripping an egg. Yeah, it's a delicate object, So we successfully produce this gripper using heat stimuli. The next one that I want to show the result is this is only about 1 year ago. So now we want to apply heat through the conductive wire. The previous one we use hot water. Now we want to apply heat stimuli using the conductive wire. So we have this kind of setup to set up, and this is the top view of the finger. So we use the same finger design as the previous one, and we use Nitronol wire and also copper wire to give heat conduction into the PLA specimen. So we use 2 and 3 power supply, and we measure the temperature at this wire using a thermocouple, and we record the reading. So we apply 2 wire perpendicular with the finger and 3 wires like this. So this is the side view of the setup of the experiment. So in here, basically we measure the deflection angle, which is this alpha. So we measure from the horizontal line into the this bending, and also we measure the deflection radius. Yeah, so this is the radius that we set. So there are 4 experiments that we perform by combining different number of wire and also number of power supply. This is one of the result for experiment 3, where we use a perpendicular Nitronol wire. We use 3 power supplies, so each power supply will apply to 1 wire, and we use 4 ampere. 4 ampere. This is the initial condition. So this is the thermocouple, this is the copper wire. Okay, and then after that, after 1 minute, we apply the current. It starts to bend. After 2 minutes, it's bend even more. After 3 minutes, 4 minutes, and we stop at 5 minutes. So then after that, we measure the deflection angle in here and also the radius. So this is how we perform the test. So after that, we collect all the data for different time and different experiment. So then we plot the temperature in here with respect with time. Okay, and we also this is for different set, experiment 3 and experiment 4. This is the temperature at the wire. Yeah, so T1, T2, T3. So this one is the T1, T2, T3, and this is the deflection angle. Again, we also curious whether the fin give effect or not. We can see without the fin, you can see the deflection is quite high, but then you can see the shape is like bending only at this point, while by having fin, it helps to create some curve in here. We also try to change the set, like making it upward of the fin, and we compare with our downward fin, and you can see also in here the upward fin is not as good as downward fin in terms of the deflection angle and the radius. So then from here we get the conclusion that the optimum parameter to achieve the best deflection is for the current 4 ampere, and then with 3 wires and 3 power supply, which is each wire will get or connected with 1 power supply. So the fin also provide better deflection compared to without fin. So this result is now is in submission. We are still waiting for the response from the journal. So this is the last one that we just finished. So we try to use 4D printing to create a package, but it's small package. So we try to control the folding mechanism of this design. Yeah. So the final target is how to make something like this as a package, like for example in the medical industry. Yeah, you can use that. So basically, we perform like fundamental or basic simple shape like this. Yeah. So the objective in here is to measure how big the angle of this deflection. So we apply the conductive wire in this bending area. So this is the printing parameter. This is the side view of this. Yeah. So basically our sample is like this, and we have this bending area where you can see the small hole in here is used to pass through the wire. So we have a constant parameter for 3D print, and then we do variation on the dimension of this bending area. So we combine the length, this is the length, and also the radius of this. Okay, so then we have this 9 combination of experiment, which is length and radius. So this is the setup that we use. This is the top view. Basically, we have power supply, and then we apply the connect power supply to the national wire in here. This is the specimen. So we also use thermal imager to capture temperature, and the side view is basically what we are going to see is in this area. So this is one of the experiment where also we measure the temperature of that specimen. This is the video I want to show. So okay, as you can see, as the temperature increase, then it start to be softened in this area. Then when it's soft, then it start to bend, mainly due to the gravitation. You can see because we put some fin in here to help the gravitation. So finally, we can see that this specimen is bent. So from there, we measure the angle, the deflection for different parameter. Some of the specimen are still like tearing because of the, you can see in this slide, there are some tearing of the bending area. So some specimen maybe because of too thin, so then it is tear, and so it damage. Okay, but some show some good result. Then we can conclude that with length 8 millimeter and radius 8 millimeter with fin, it produced the lowest angle, which is about 92 degrees. We also do the cycle test in order to measure, to make sure that we can do consecutive or we can apply this technique few times. So from the cycle test, so we hit up once and then we heal, which is we hit up again, so it go back to original, and then we heat up again, so you can see the angle is changing. So we still need to improve this cycle test. Yeah, and we also make this combined specimen test in order to replicate the package shape, and then we also do the cycle test. Yeah, so this step is still in the process. So this is some result that we already have from this work. The last work, we can conclude that this dimension show a good result compared with other dimension. We still need to perform the long-term cycling test, yeah, in order to make sure that it is repeatable. Okay, I think this is the end of the my presentation. So before I end, I want to give some summary about the 4D printing technology. It's basically with this technology we can save some fabrication costs, because now you can combine different shape in one process, and by applying the stimuli you can also change the shape without additional for example mechanical force. This also can simplify the fabrication process. Yeah, so you can simplify the assembly process, and also you can combine this with different material. So for example, some are SMP and some are not SMP, so you can see the effect between the combination of this SMP and without SMP material in order to improve the for example the structure or the shape changing mechanism of certain product. Okay, with this, I think I will end my presentation. Thank you so much for the time. I will go back to the moderator, Prof. Thank you so much.
Thank you, Prof. Saptaji, for your insightful sharing. So from this presentation, we do realize that today's discussion highlighted the evolutions from the traditional 3D printing methods to the emerging frontier of the 4D printing. And we also explore the real-world application in automotive, healthcare, or even food, as well as some research breakthrough in the orthotic spinal fabrications or photopolymer optimizations, as shared by Prof. Saptaji just now. So again, from this presentation, we also understand that what stands out is how 4D printing, with its smart materials and dynamic adaptability, not just an extensive of 3D printing, but it looks like a paradigm shift for us, opening doors to responsive, sustainable, and multifunctional designs. And we also look at the future of the manufacturing is clearly moving towards these intelligence as well as adaptability of these 4D printing. Of course, now I open up the floor for the question and answer sessions. You may either unmute yourself to ask the questions or even type your questions in our chat box here, for which now I have already got 3 questions in the chat box for Prof. Saptaji to answer. Let me go through this question one by one here. The first question is from Andre, that he asked that on the design of experiments, how do you set different deformation temperatures? Is it a material with different properties?
Okay, thank you for the question, Andre. So basically, the deformation temperature, which is I have seen, I have shown in here, is, you can see it depends on the material. Yeah, for example, PLA, it will start to deform at higher than TG, which is the TG of the PLA is about, I think, higher than 65. It starts to be softened. So normally it depends on the material itself. So yeah, And for normally we do the experiment for PLAs at about 85. Yeah. So maybe different material will have different TG. So you need to check their TG temperature. Okay. Is it answered?
Thank you.
Okay.
I was going to ask you
Yeah.
though, specifically for the research project that you had for the 4D research project. I was specifically asking on that design of experiment. I just wanted to understand that you had the different temperatures. If you go to that slide.
Which one?
If you keep
This
going
one?
forward. Oh, yeah, that's the one there. Yeah.
Yeah.
So when it says there
Okay.
deformation temperature and recovery temperature, is that something that was set on the design of experiments, or is that dependent on the material itself?
Yeah. So this is set based. I mentioned before that based on the material. So at the at this set, we use quite different gap for the temperature in order to know the effect of the temperature more significant. So we set 55, 80, and 60. So then 80 is the highest. So we want to see what is the effect of the temperature. Is it more significant when we apply the difference of the difference of the temperature is quite high. So this also based on the reference that we have. So some reference use 55, 60, and 80. So then we use this temperature in our experiment. So there are two method that we think we need, that we think we apply in here, that based on the reference and also based on the gap of each of the temperature that we need to apply. Okay.
That makes sense now. Thank
I
you.
hope it does. Yeah.
Okay, thanks, Andre, for the questions. And the next question coming from Engineer Chua, of course. He asked that, can the current printing technology accommodate two or more stimulus, say heat and light combinations?
Yeah. Some material will have two stimuli that can apply together. Yeah. But so far, what I have read and what I have found in the literature is normally they apply only one stimuli. But there's a possibility that we can apply both, for example, heat and light, or heat and heat and pH maybe. Yeah. But so far I haven't found about this combination. Maybe we can try in the future about this.
Okay. All right, thanks for the answer. And of course, the next question is, now we are in 4D, and how will 5D or even 6D be like?
Yeah, this one I don't know. So far, I only reached to 4D printing. So I still haven't found about 5D printing or 6D printing. But normally, if we talk about the axis in the process, like for example, in the machining process, yeah, we have 5-axis machining, yeah. So perhaps some also have some argument that 4D printing is basically we have 4 axes of printing, like X, Y, Z, and maybe the rotation. So yeah, in terms of 5D printing, there might be there might be understanding about that concept by using the 5 axis. But in terms of the like additional stimuli, maybe I don't know about that yet. Yeah.
Yeah, yeah, yeah. Oh, wow, well, listen to your explanation. I just went through my mind that in the earlier days, I also read something about this self-healing materials. I'm not sure whether there will be something for 5D or 6D as well. It could be something in future as well.
Yeah, but yeah, self-healing is also included as a 4D printing because it's
Okay.
the, the the 4D is the time, so it
Mm-hmm.
heals in the period of time.
Yep, yep.
Yeah,
Okay.
but we don't know. Yeah.
Right. Right, so at this moment, can I invite any questions from our audiences here? If you have any question, you may just unmute yourself and ask a question. Or even if you want to, you can type on the chat box as well, which I can convey the message for you. Right, while waiting for any questions, I have a questions over here from myself that I'm thinking that given the rapid rise in the 4D printing research and applications, what do you think will be the biggest barrier to its widespread adoptions? Would it be materials, cost, or even programming complexity?
Hmm. Okay. I think the challenge is to convert the um, experimental or lab scale into the industrial
Mm-hmm,
scale because like
mm-hmm,
uh, you you see from my latest research where we want to make 4D printing as a packaging.
yep,
So it is in the small scale, but how to enlarge or to make it into the industrial
mm-hmm.
application. Uh, this is, I think, still challenging for me. Yeah. In terms of material, I think it's already settled. The material properties itself is already there, but how
Yep,
to make it more complex, like you mentioned, also maybe it will be the challenge.
yep. Sure, sure. Thanks for that. Right. Can I have a last call? Is there any other questions? Oh, yes, there's one more questions coming up from Andre again. And will the slides be available for the future reference? Not
I
sure
can
whether
share the
you're open to
slides.
sharing the slide.
Yeah,
Yeah. Okay.
yeah, I
Yep.
can share the slide later on.
Thanks. So while waiting for
Maybe
that, yep.
any question from my students?
All right. Any other questions?
Yeah, no question.
No questions. Let me cross-check the chat
Doc-
box. No. Oh,
Dr.
yes.
Kus, can I ask one more question? Because,
Yes, of course.
okay, okay. So now that I think 4D printing is still probably new because it's really not yet really not yet matured like the 3D printing lah. Okay, so I've seen some examples of applications where you can actually do like the gripping and all this.
Mm.
Apart from those things, where else can we actually use the 4D printing in your opinion? What are the things like in where we can use? Because if you see that just now in 3D printing, I see some food applications, I see some applications in the medical. Okay, so where else can we use it?
Yeah, the most research that performed for this 4D printing is the gripper, as you mentioned before. Um, but you can see in here, it also can be used for the prosthetic, yeah, for the medical industry, yeah. But in yeah, I don't know yet in more specific of the other application, but mostly what in the reference is about this gripper mainly. But you can see also it can be used for microfluidic, for example, to analyze, for example, the milk. This is one example. So maybe you can check the food inside the container. So we have some like indicator or sensor using this, for example, pH stimuli, where we can check whether the food inside of, for example, meat, milk, is it already expired or no, by like having a color indication. So we can also use for food industry to check their expiration or their availability, yeah, by using pH stimuli, something like that.
Okay, thank you so much, Dr. Kus.
Yeah.
Okay, thanks again. Prof. Saptaji also sent out his email address in the chat box. If you wish to require the slides from from him, please email to him at this email address in the chat box. So with this, we come to the end of our presentation today. Once again, much appreciated to Prof. Saptaji for your really meaningful, insightful sharing and answering all the questions from all of us. And before the end, we'll need to take a group photos. So can I hand over to Chua to coordinate this?
Okay, so can I have all the participants or all the audience to probably turn on your camera for a short while so that I can capture you all? Come. Wait, just give me a second. A few more. I see quite still. Okay, all right, that will do.
Once again, thank you, everyone. Of course, we do have a few more coming up in the next Saturday and the Saturday after. So stay tuned with all the updates as well as join us for the next few series of this seminar. And thank you and have a very great weekend ahead to everyone.
Thank you. Bye.
Thank you so much.
Thank you very much.
Thank you.